lesson, we are going to be looking at the structure of the atom. And the first question that we would ask is, what kind of subatomic particles are our atom made up of? Now, as you would remember from integrated science back in first and second form, or even in third form chemistry, the atom is made up of these subatomic particles. We have neutrons, protons, and electrons. And as was stated in our previous class, the model of the atom that we still use today would be the Bohr's model of the atom, the planetary model, where we have our electrons that are orbiting on our shells, or what we call orbitals, with a centralized nucleus, a very dense nucleus. And here is a table that would look somewhat familiar to you. Now, this table, it is going to represent the masses of the electrons, the protons, and the neutrons. And as you can see, the mass of an electron is significantly smaller to that of a proton, so much so that if we are to look at ratios, and if we are to consider a 1-to-1 ratio, all right, looking at the proton and the neutron, we're going to realize that both of them would have the same ratio. All right, both of them would have the same mass of 1.67 times 10 to the negative 27 kilograms. It's a very important number. We're going to look at that number a little bit later on. But we're also going to realize that the mass of the electron is 9.1 times 10 to the negative 31 kilograms, which is significantly smaller. And so if we are to look at ratios, we're going to see as 1-to-1 for neutron to proton, and from proton to electron it will be 1/1/1800 or something of the sort, a number like that, significantly smaller, so much so that we're just going to consider it as 0. And if we're looking at the relative sizes of the proton and the neutron compared to that of the electron, we will realize mathematically that it is 1,700 and something times bigger than the electron, that is the proton and the neutron. All right, which is why we have this approximated value right here of 1,800. Now, although the masses are insignificant, we cannot downplay the importance of our electron, because our electron actually has a big charge. It's a very small thing that packs a big punch. All right, and the charge on the electron is negative 1.6 times 10 to the negative 19 coulombs, which is able to fully balance out the proton, which is significantly bigger in size, but equal in the magnitude of the charge, which is positive 1.6 times 10 to the positive 19 coulombs. And so we will now look at our atomic notation. When we look on our periodic table, this is essentially how our elements are presented. Now, what we need to remember is that our atomic number is actually a summation of our neutrons as well as our protons. What is the significance in me telling you that? The significance is that this number will be a big number. So this is going to be a big number. Well, or a bigger number to that of the atomic number. Now, this may be a little bit misleading, because if you look in some of your chemistry labs, you're going to realize that sometimes you may have an element written like this. So it is carbon 12,6, or you may look on other periodic tables and you may see carbon 6,12. Now, what you need to take away from this is that the bigger number, which would be the 12, would end up being our mass number, whereas our smaller number, which would be the 6, would end up being our atomic number. And we're also going to remember that our atomic number actually gives us an idea of the amount of electrons that are orbiting that nucleus. So if our atomic number is 6, then we are going to represent our stable atom as having 6 electrons orbiting the nucleus. And so we have it here that the atomic number or proton number is the number of protons found in the nucleus, and the chemical property of an element depends on the number of electrons. The number of electrons may change in chemical reactions, but the number of protons will always remain the same. The atomic number or the nucleon number, which is given by A as seen above, is the number of nucleons found in the nucleus. The nucleon refers to the protons and neutrons in the nucleus. And so we shall continue. Now, here's a very interesting number. This is called the atomic mass unit, and it's a very important number. Now, if you look at this number, you are going to remember, or you're going to realize that this number here, this 1.67 times 10 to the negative 27 kilograms, is actually the value of the mass of a proton or the mass of a neutron. And so what we need to now understand, and I'm going to be using back my carbon with a mass number of 12 and a proton number of 6. Whenever we see this 12 represented up top, it is really saying 12U. That is what it's really saying, where the U is going to be our conversion factor. So if you get a question that says an element carbon has a atomic mass number of 12, convert that atomic mass number to mass in kilograms. All you're going to now do is multiply 12, which is the mass number, by the atomic mass unit, which is 1.67 times 10 to the negative 27, in order to get your actual mass in kilograms. So that's 1.67 times 10 to the negative 27 multiplied by 12, which will give you 2.004 times 10 to the negative 26 kilograms. And as we get further and further into the topic, we're going to see the significance of knowing what this is. Now we have a note here that says that atoms may lose or gain electrons. However, most of the time, the atom is electrically neutral. This means that the number of protons in a nucleus will be the same as the number of electrons. And so we move on to the periodic table, something that we're all familiar with. All right. And some students may have asked the question, sir, how many elements in the periodic table am I supposed to know for a physics exam? You don't need to memorize the elements in the periodic table. However, it is good to always know, as science students at the grade 11 level, it is good to know at least the first 20 elements. I remember memorizing this from when I was back in high school: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. I remember these things, so much so that I may know a few more, but here we go. And our periodic table is actually grouped up into elements. The elements in the periodic table are grouped up into periods and groups. Okay, so periods are our rows. All right, so our periods go across in rows, and our groups go down in columns. And there's several information that the periods and the groups can tell us. All right. Everything that is in the same group will have the same amount of electrons on the outer shell. Everything that is in the same period will have the same amount of shells. And so there are little trends that we can pick up with groups and periods. And so here we have an exercise. And at this point, I'd want you to pause the video 1 second to see if you can fill this out. And after filling this out, you're going to realize that you would have done such a phenomenal job and that your table would pan out to look a lot like this. Now, in some books, this is just something to note. In some books, you're going to realize that whenever you see group 8, some of them may refer to it as group 0. So group 8 sometimes can be referred to as group 0. And so we now want to move into this thing called isotopes. And isotopes of the same element have the same number of protons in the nucleus, but it actually has a different number of neutrons. So it will have the same number of protons, because remember now, the protons are the atomic number, and any element that has the same atomic number is the same element. Yeah, once you change that atomic number, you are moving from one element to the next. However, you don't have to have the same number of neutrons in your different isotopes. And here are some examples. For hydrogen, we have hydrogen 1, 1, where in this first example, we have only one proton in the nucleus, but no neutrons. In this isotope of hydrogen, deuterium, we have one proton and one neutron, giving it a mass number of 2. And in the other isotope of hydrogen, tritium, we have one proton but 2 neutrons, giving it a mass number of 3. In all cases, though, you would realize that all of them are hydrogen by virtue of having the same atomic number of 1. Here's another example. And for this one, we are looking at carbon, 2 isotopes of carbon, one of them being carbon 12 and the other one being carbon 14. There's a slight error in this. The slight error is, for the isotope carbon 14, this should not be 12 neutrons. All right, this should be 8 neutrons. And so let us look at it. And by the way, if we wanted to know the amount of neutrons that are actually in this isotope, then what we could do is we could say, okay, if our mass number is really the number of protons and the number of neutrons, if we know that we have 6 protons and if the mass number is 14, then simple algebra would tell us that 14 minus 6 would give us the number of neutrons. And so here we go. Here is a CSEC style question. Not only is it a CSEC style question, this question has come on CSEC before. So we start off by saying the atomic number of chlorine is 17. How many protons are there in one atom of silicon? And so what they would have done is they would have given us 17 as a reference number. And it simply now means that if I want to figure out the number of protons that are in silicon, I now have to count going to my left. So if this is 17, this would be 16, this would be 15, and this would be 14. Therefore, the amount of protons, which is the same as my atomic number, is 14. The next question is, the most common isotope of boron may be represented as boron 11.5. A boron atom has 2 shells of electrons, with 2 electrons on the first shell. In the space below, well, there's no real space. In the space below, draw a clear diagram to represent the number and distribution of protons, neutrons, and electrons in a neutral boron 11.5 atom. All right, now that is a third form chemistry question. There is no issue with that one at all. And so here we go. I'm going to start off by writing my information that I have. So for boron, I'm going to say that I have 5 protons. So proton is equal to 5, and therefore my neutrons would be equal to 11 minus 5, which would be 6. And I'll draw a circle around that one. And then I'm going to draw my first shell. And third form chemistry is going to remind you that your first shell will have a maximum of 2 electrons, which means that my second shell will have only 3 electrons, because 3 plus the 2 that I just accounted for would be equal to 5. So I'll draw 1, 2, and 3. So I'd have my electrons distributed like that. And I'll also go as far as writing the electronic configuration. So my EC would be equal to 2, showing the amount of electrons on my first shell, and 5, 2 and 3, the amount of electrons on my second shell. And the final part of the question says, write the symbol for another possible isotope of boron. All right, that's not a problem. If I'm going to be writing the isotope of boron, I have to start off by writing the symbol. Then I have to write my atomic number, which is 5. And perhaps another isotope of it could be boron 10.5. Yeah, another isotope. And I said another. All right, because another isotope could also be boron 12. So it could be boron, write down the 5 down there, and I could probably write 12. And there are a lot of possibilities that you could write. Remember now, CXC is asking you for a possible isotope of boron. They're not expecting that you will know all the isotopes of every single element, because as we would have learned yesterday, there are over 3,000 radioactive isotopes, and those are just the radioactive ones.